In the last lecture, we completed the introduction of rectifier circuits. In this lecture, I will explain half-wave rectifier. In case of half-wave rectifier, only one half of the AC voltage is rectified. For the other half, we get zero voltage. This is what happens in case of half-wave rectifier. For the first half of the AC voltage, we have rectified output, and for the other half, we get zero voltage. This is the circuit of half-wave rectifier. Vi is the input voltage, input AC voltage. This is the diode, and we are measuring the output voltage across resistance R. In case of positive half cycle, this will be the polarity of input voltage Vi, and diode will be forward biased because P side is connected to the positive terminal and N side is connected to the negative terminal. I will replace the diode with its equivalent model. I am considering piecewise linear model, and in case of piecewise linear model, we replace the diode with barrier potential and the diode resistance RD. This is the polarity of barrier potential, and let's say current through the resistance R is equal to I. I will use Kirchhoff's voltage law and try to obtain current I. We have plus Vi minus VB minus IRD minus IRD, because drop across the diode resistance is equal to IRD. Then we have minus IR drop across the load resistance equal to 0. So current I is simply equal to Vi minus VB divided by RD plus R. This is the value of current I, and we can easily calculate the output voltage VO. This is equal to IR. So we have Vi minus VB divided by RD plus R multiplied by capital R. We can also write this equation like this: V output is equal to R divided by RD plus R multiplied by Vi minus R divided by RD plus R multiplied by VB. This is what we have in case of piecewise linear model. Generally, the diode resistance RD is smaller than the load resistance R, and we can neglect the diode resistance RD, and once we neglect the diode resistance RD, the output voltage VO is equal to Vi minus VB. This is what we have in case of positive half cycle. The output voltage is equal to input voltage minus barrier potential, and VB is equal to 0.7 volts for silicon and 0.3 volts for germanium. Now we will find out the output voltage in case of reverse bias condition when diode is reverse biased, and diode will be reverse biased when the polarity of input voltage is like this, minus plus. I will replace the diode with its equivalent model, that is the open circuit. As the circuit is open, there will be no current, and current I is equal to 0. So simply the output voltage is equal to 0 volts in case of negative half cycle. And that's what I told you initially. Only one half of the AC voltage is rectified, and we have output voltage equal to Vi minus VB. For the other half, we get 0 voltage. For the other half, we are having output voltage equal to 0. Now we will plot the waveforms. The first waveform is for input voltage Vi. The peak voltage or the maximum voltage is equal to Vm, and Vb is the barrier potential. I will mark Vb, the barrier potential of the diode, and depending upon this barrier potential, we will get the output waveform. I will extend this line like this. This will help us to plot the output waveform. For the positive half cycle, the diode is forward biased, and output voltage is simply equal to Vi minus Vb. I will plot the output voltage for the first half cycle, that is the positive half cycle. When the input voltage Vi is less than Vb, that is the barrier potential, the diode will remain off, because diode will be on only when we overcome the barrier potential. So initially diode will remain off when Vi is less than Vb, and for this reason Vi is less than Vb, then we have the plot like this, in which the value of output voltage is Vi minus Vb. This means the peak voltage that we are getting here is equal to Vm minus Vb, and again when Vi is less than Vb, the diode will remain off and output voltage is equal to 0. For the negative half cycle, the output voltage is equal to 0, so we have 0 as the value of output voltage. This plot is for output voltage Vo. After this, we have the same plot for the next positive half cycle. We have the same plot for the next positive half cycle. The diode will remain off when the input voltage is less than the barrier potential, and it will be on when input voltage is greater than the barrier potential. So this is how the output voltage waveform will look. This waveform is for the piecewise linear model. If we consider the ideal model, then the barrier potential Vb is equal to 0. So the output voltage is simply equal to V input, the input voltage, for positive half cycle, and output voltage is 0 for negative half cycle. So if we plot Vo for ideal diode, then we have the plot like this. In positive half cycle, the maximum voltage is equal to Vm, and the diode will remain off. And again we have the identical waveform as the input voltage, and for the negative half cycle, the diode will remain off. So this is how the waveform will look for ideal diode, and I will use this waveform to obtain the expression of average output voltage. The output voltage for the positive half cycle when omega t is from 0 to pi is given by Vm sine omega t, because we have sinusoidal waveform. This is when omega t is from 0 to pi, and when omega t is from pi to 2 pi, the output voltage Vo is equal to 0 volts. This is when omega t is from pi to 2 pi, and I will obtain the average output voltage by integrating the waveform from 0 to 2 pi, that is the one time period. I will integrate this waveform for one time period, and the result is average output voltage. So let's do the integration. I will represent the average output voltage by VAV, and it is equal to integration from 0 to 2 pi Vo d omega t divided by 2 pi minus 0, and this is equal to 1 by 2 pi. Inside the bracket we have integration 0 to pi. When omega t is from 0 to pi, Vo is equal to Vm sine omega t. So we have Vm sine omega t d omega t plus integration from pi to 2 pi. From pi to 2 pi, Vo is equal to 0. So we have integration of 0, and integration of 0 is equal to 0. So we are left with 1 by 2 pi integration 0 to pi Vm sine omega t d omega t. Vm is constant, so we have to integrate sine omega t. Vm divided by 2 pi. Integration of sine omega t is minus of cos omega t. Lower limit is 0 and upper limit is pi. So finally we have Vm divided by 2 pi inside the bracket minus of cos pi, the upper limit, minus of cos 0. When you solve this, you have Vm divided by 2 pi multiplied by 2, because cos pi is equal to minus 1, cos 0 is equal to 1, so we have 1 plus 1, which is equal to 2. So V average is equal to Vm divided by pi, or I can write Vm divided by 3.14, and this is equal to 0.318 Vm. So the average output voltage is equal to 0.318 of Vm, the maximum or peak voltage. Now I will derive the expression for average load current. I will use the expression of average output voltage. Average load current, I average, is equal to V average divided by R, where R is the load resistance. V average is equal to Vm divided by pi divided by R. So this is equal to Vm by R pi. Vm by R is Im, the maximum value of load current. So we have Im divided by pi as the value of average load current. There are few more expressions, but I will not derive them in this lecture. In this lecture there are only two expressions. First one is the average output voltage, which is 0.318 of Vm, and the second one is average load voltage, which is Im divided by pi. I will end this lecture here. If you have any doubt, you may ask in the comment section. In the next lecture we will derive the remaining expressions. So see you in the next one.